Hi, welcome back to Statistics 1. We're up to lecture 11, and the topic today is multiple regression. So this lecture is divided into 3 segments. In the first segment, I'll just introduce you to some basic concepts in multiple regression. We've already covered simple regression, and you saw a glimpse of multiple regression, but we'll get into it a little bit more deeply in this first section. In the second segment, we'll sort of take a detour basically just into pure math, and I'll introduce you to matrix algebra if you haven't done matrix algebra before. And the reason I'm doing that is to understand how the regression coefficients are estimated in a multiple regression. You sort of have to have at least a basic understanding of matrix algebra to see how these are estimated all at once. So we'll do a little bit of matrix algebra in the second segment, and then in the third segment, we'll walk through how the regression coefficients are estimated in this larger regression equation that includes multiple predictors. So first, segment 1. Let's look at multiple regression, just sort of an overview. And again, the important things to take away here are the components of the multiple regression equation, and sort of most importantly for this segment, how to interpret regression coefficients when there are multiple coefficients in the model. And this is a difficult topic that even advanced researchers sometimes mix up and make mistakes on. So I'm going to take my time and really try and reinforce how to interpret these coefficients. So again, just to make this distinction between simple regression and multiple regression, real easy. So simple regression just has one predictor in the model. Multiple regression, you can have as many predictors as you want. So here's the multiple regression equation. You saw this when we first talked about regression about a week ago. I'm just putting in more predictors. We're going to estimate multiple betas. So to be clear, we're going to have a predicted value on the outcome variable y. We still have a regression constant. That's just the predicted score on y when all the x's are 0. We have a bunch of predictor variables now, which means we're going to have a bunch of unstandardized regression coefficients. We still have residuals, so we're going to get one predicted score for each individual, and each individual has one observed score, so we just have one residual per person. And I'm using k here to denote just the number of predictors in the multiple regression equation. We still can calculate a multiple correlation coefficient because remember, that's the correlation between the predicted scores and the observed scores. And this is a way of evaluating the overall model. And we can square that multiple correlation coefficient to get r squared, and that tells us the percentage of variance in the outcome measure that's explained by the model. And again, that's a way to evaluate the overall model. It's a way to compare competing models. The example I'm going to use for multiple regression is one in which we predict faculty salary from a series of predictors. So what are some things that might predict a faculty member's salary? Well, one obvious one, and it is the strongest predictor in this example, is just time since the person's PhD. So people who have been out of school longer, been working longer, they tend to make more money. But another predictor is how many publications, particularly peer-reviewed publications, an individual has. So if a faculty member is really prolific and publishes a lot, that means they tend to be very marketable, and their salary is probably much higher. So we could expect probably a positive correlation between number of publications and salary, and possibly gender. Unfortunately, particularly in the past, but even to this day, there's some slight gender inequity. You might see a difference between men and women. So we could look at that in this regression equation. So first, I'm just going to show you some summary statistics because you'll see when we interpret the coefficients, you can sometimes lose sight of the actual summary statistics because you will see some discrepancies. So first, let's just look at some summary statistics. I'm borrowing this example from a previous example, which is now a little outdated. These are US dollars. So if you're in the US and you are envisioning a career in academia, don't worry, it gets a little better than this. This is an older example. So the average salary for professors in this example was 64,000 with a standard deviation of 17,000. Time since the PhD was about 8 years. So these are relatively young faculty members. It's funny, when I used this example years ago, I didn't think 8 years out was young. Now I do. 8 years out is young, with a standard deviation of about 5 years. And they have, on average, about 15 publications with a standard deviation of about 7.5. Also, because gender is a nominal variable, remember, we haven't really dealt with this situation yet in regression. We can't just throw in a nominal variable into a regression equation without giving it some code, because R, when it runs that LM function, it needs a numeric value. So we need to code male and female somehow. So I just coded male as 0, female as 1. That's just arbitrary. You could do it the other way, it doesn't matter. So if we ran this in R, we would use the LM function. Same thing as regular regression, we just add in more predictors. So I did LM, salary is the outcome measure, so it's salary tilde, and then all your predictors. Time plus pubs plus gender. Notice see the GLM in there. We covered the GLM, it's right there. It's Y is a function of these predictors, time, publications, and gender. I ran that in R, and here's my output. So I get 46,911 plus, and those are the slopes relating each individual predictor to the outcome measure salary. But let's really think about what these numbers mean, and I'm going to ask some questions to get you to think about this. Sorry, before I do, I did summarize all those coefficients in a table of coefficients. So you'll see this in your R output. Actually, you've seen this when you did simple regression, but when you do multiple regression in R, it'll look a lot like this. You'll see first the unstandardized coefficients. So that's in the first column. Those are unstandardized coefficients. So to be clear, like 46,911, that's the predicted score on Y when all X are 0. And these are the individual slopes for each predictor. You have a standard error associated with each one of those. Remember, because each one of those is just a point estimate. Now that we've talked about confidence intervals. T is just the unstandardized regression coefficient over standard error. I'm using beta here to reflect the standardized coefficient, and I just put that in so you could compare them. And then you get a p-value associated with each one. And then down here again at the bottom is just the overall regression equation. Now let's get to those questions that I talked about. And I'm asking these just to get you to think carefully about this output and this outcome and what these coefficients really mean. So what is 46,911? What is 502? If you look back at the table, you could ask who makes more money, men or women? According to the model, is that difference between men and women, is it statistically significant according to this model? What's the strongest predictor of salary? Well, let's answer those. So 46,911 was the regression constant. What is that? It's the predicted score on Y when all the X's are 0. So it's when someone has no time since their PhD, so they just graduated, they have no publications, And what was coded as 0? Well, I coded men as 0. So 46,911. If you think back to the summary statistics, that's a really low salary. Why is it so low? Well, because it's the predicted salary for someone who just graduated and has no publications and is male, because I coded male as 0. Okay, so that's how to interpret the regression constant in this example. What's 502? Well, 502 was the regression coefficient for publications. So you might say, well, okay, that's for a 1 unit increase in publications. That's the predicted change in salary. And that's almost right, because that's what we learned in simple regression, right? The regression coefficient is for a 1 unit increase in X, it's the predicted change in Y. It's the slope relating X to Y. But what you have to remember in a multiple regression is that there are other variables floating around in this model. So it's the slope relating publications to salary, yes, but it's the slope at the average level of time since PhD and averaging across men and women. So it's taking into account those other variables in your model, which can get tricky and fool you if you're not careful in interpreting the regression coefficients. So for example, who makes more money, men or women? Well, if you look at the p-value, it's not significant and it's negative. So if you go back and look at the table of coefficients, it was like negative 3,000 something. I coded men as 0, women as 1. So a 1 unit increase in X means you're going from male to female, and the predicted change is negative. What that means is who makes more money, men or women? Well, women, I'm sorry, who makes more, men, but there are other variables floating around in the model, right? That's the difference between men and women for an average number of years since the PhD and an average number of publications. So who makes more money, men or women? I don't know, actually, because I didn't look at just average salary for men and just average salary for women. I looked at it in the context of these other variables. What if all the female faculty members in this sample were just hired and their time since the PhD is very low? Then we might get this relationship between men and women just because of other characteristics of the sample, that is, other values on the other variables that are used as predictors in the model. That's where this gets tricky. Then, according to this model, is that difference statistically significant? If you go back to the table of coefficients, the p-value is not less than 0.05, so no, it's not significantly different. Does that mean there's not a significant difference in salary between men and women in this sample? No, because again, this is the difference between men and women when taking into account these other variables. It's very likely that there are more men that are at the higher end of the distribution in terms of years since PhD, right? Because in academia, there are more men than women, especially years ago. So if we took that variable out and just looked at the difference between men and women, it might be significant. So that's where this gets really tricky. The final question, what's the strongest predictor of salary? Well, time since PhD. I sort of gave that away at the beginning. But how do we know for sure? You have to look at the standardized regression coefficient, not the unstandardized, because the unstandardized is linked to the scale of each predictor, right? So to compare different predictors, you have to look at the standardized regression coefficient. That's why I added that column, so we could answer this question. That had the highest standardized regression coefficient, so that's why time is the strongest predictor. So to wrap up this segment, Again, just understand the components of the regression equation, which I think should be clear by now. But more importantly, maybe walk through this lecture a couple times to make sure you understand how to interpret the regression coefficients when there are multiple predictors in the model, because it can get tricky. And we'll do more examples of this in lab and next week in the context of moderation and mediation.